In this lecture we will introduce the concept passivity, which is a very useful tool in understanding the stability behavior of interconnected systems from the input-output point of view. The concept has very strong, solid foundations coming from some physical systems. So that means there are many ways to motivate this concept, passivity. Okay? And one way, not surprisingly, to motivate passivity is through electrical networks. Okay? So we will now try to make a simple observation from using a simple circuit, and then we're going to generalize that observation to the definition of the general definition of passivity. Okay. So motivation is electrical networks. Okay. Now consider the one port RLC network. Okay, let's call it N. And then we're driving this network by a voltage source. That's our input. Let's say the S source. That voltage will generate a current. Okay, let's go into the one-port network. Now the circuit N, okay, our network is said to be passive. Okay, this is one way to see the concept. If the energy absorbed by the network during some time interval, okay, from 0 to capital T, let's say, during any time interval, okay, from 0 to some time, is no less than the energy stored by the energy storing components for electrical circuits. Those are capacitors, inductors in general. For mechanical systems, energy can be stored through springs. Okay, you compress the spring and some potential energy stored there, or you raise some mass up, okay, and then you can store energy in terms of gravitational potential energy, and so on. In the network, over the same interval, from 0 to T. Okay, so let's try to visualize this statement here through a simple example. Where we have a series RLC, one port, okay, and it's driven by some voltage source. What I mean is, we're talking about this topology. Okay, so this is the input, the voltage provided by the independent voltage source Vs that generates a current I that flows through the one port. And we have linear components R, L, and C. Energy storing components are the capacitor and the inductor, and the energy stored is for the capacitor proportional to the square of the voltage appears across its terminals, and for the inductor it's proportional to the square of the current passing through the coil. Now in this configuration, the current that we see at the input terminals and the current that's flowing through the inductor are the same. Okay, so for this simple circuit, let's figure out, or let's write down the absorbed energy and the stored energy. And then once we have absorbed energy and stored energy, we can check, we can apply this definition of passivity here, informal definition of passivity here, and see whether that network is passive or not. So what's energy absorbed? Now, energy absorbed is the same as the energy that's produced or delivered by the input, by the source. And it's simply the integral of the power. And the power that's delivered by this source is simply its voltage times the current that's extracted from the source by the 1 volt. So what we're talking about is the integral of the power, which is a product of voltage and current. As for energy stored, during the interval from 0 to capital T is total stored energy at time T, capital T, by the energy storing components, namely the capacitor and the inductor, and that minus the initial energy, which has to do with the initial conditions of our dynamic components. Where the energy stored in the capacitor, as you all know, is 1/2 C times the voltage square of the capacitor, and for inductor we have the dual expression. Okay, 1/2 replace capacitance by inductance and replace voltage by current. L squared. Okay, now for this circuit we're going to figure out these, and we're going to figure out the energy absorbed, and then we're going to check whether this thing can ever be larger than energy absorbed or not. If it's not, then we're going to conclude that our network is passive. Okay, let's begin our analysis. Let input be denoted by the notation U, and in this case input is voltage provided by the external source, voltage source, and the output is denoted by Y, and it's the current extracted by the RLC circuit from the source. Okay, it's simply I, or the inductor current, because they're the same by KCL. For this system, let's obtain a model, and usually it's, when we have a physical system, usually it's meaningful to work with physically meaningful state variables, and in this case, best candidates seem to be the capacitor voltage and the inductor current. So let's choose our states as x1 as IL and x2 second state variable as the capacitor voltage VC. What's the model? Okay, so we require x dot, x is our state vector x1 and x2, x that equals some function of x and the input. So we require, that would be our system, okay, or the model. To obtain that model, we use, okay, we can use, for is KVL, which says that sum of all these four voltages must equal 0, or this Vs must equal this voltage plus that voltage plus voltage of the capacitor. Okay? So the voltage of plus minus, the resistor is R times I is IL, and IL is X1. Okay, so Rx1 is the resistor voltage, plus we have plus minus inductor voltage, which by thermal equation equals L times the rate of change of the current. The current is IL, so we're talking about that for L X1 dot. And finally, for the capacitor voltage, we directly have it as a state variable, okay, plus X2. So that's the sum of these three voltages, plus minus, plus minus, plus minus. And that must equal, by KVL, the voltage provided by the source. Okay? So that equals Vs, and Vs is U. Okay. We need another equation because Vs is the second order. And that other equation directly comes from the term equation for the capacitor. C times the rate of change of the voltage equals the current passing through it. C times rate of change of voltage. Voltage is X2. X2 that equals the current. Okay? And the current is IL. IL is our state variable X1. Okay. Now let's put these two equations in a form that we're more familiar with. Therefore, we can write X1 dot X2 dot equals A times X1 X2 plus B times U. So this is an LTI system. Minus, okay, what's X1 dot? X1 dot is minus R over L X1, and we have minus 1 over L X2, and we have what? 1 over L U. As for X2 dot is simply 1 over C times X1. 1 over C times X1. These entries must be 0. So that's X that equals AX plus BU. How about the output? Y. Y equals C times X plus B times U. In this case, Y equals X1 directly. Okay. Oh, let's write that as X2. So Y is I is IL, IL is X1, so we're talking about this C matrix. Plus du, D matrix is 0. So this whole thing, therefore, for the general nonlinear notation, is our f of xu. Okay, x that equals f of xu. And as for the output, y equals, the notation that we use is h of xu. So this is simply x1, and x1 in this case is our h of xu. And x is our state vector. Okay. Okay, now define the storage function. Storage function simply as the sum of stored energies in capacitor and inductor. Bx equals EL plus EC, and that's 1/2 L x1 squared plus 1/2 C EC squared, and EC is x2. Then we can compute, because we have the system, now the model, we can compute V dot, that is the time derivative of storage function, along the solutions of our system. And the system model is here. V dot equals L x1 dot plus C x2 dot. Okay. That equals L x1 times x1 dot, and x1 dot is here, minus R over L x1 minus L minus 1 over L x2 plus 1 over L u. Plus 1 over L plus C x2 times x2 dot, and x2 dot is here, simply it's x1 over C. Okay. So what we have therefore is, here we're going to have a minus x1, x2 term, because this L and that L will cancel. And here we have x2, x1 term, that C and that C will cancel. So there will be cancellation of this term and that term. And what we're left with is minus R x1 squared plus x1u. Remember that x1 was our output also, so we can write this V dot in terms of input and output. If you do that, we have u times y, because x1 is y, minus R times y squared. Okay. Hence, this product u times y, which in our case has a physical meaning. It's the power provided by the source or the input, equals V dot, the rate of change of stored energy in our dynamic components, capacitor, inductor, plus R times y squared, the power absorbed or dissipated on the resistor. Okay. Now, since we're talking about passive components, by which we mean positive R, L, and C, this thing is never negative. Hence, u times y is never smaller than V dot. Okay, uy greater than equal to always V dot. Okay. So that implies this integral ut yt dt is never less than this difference minus v of x of 0. Okay. So this is energy absorbed by the one part by RLC circuit, and this is the energy stored. Since energy stored is never greater than energy absorbed, according to our informal definition, formal version we will now provide, this RLC network is passive. Okay, now we're ready to generalize this simple but insightful example to the definition of passivity. Here is a formal definition that we will be working with henceforth. The system x dot equals f of xu and y equals h of xu. And we're assuming throughout that f00 equals 0 and h00 equals 0. Okay. Now this system with x in Rn and u and y, input and output, both of the same dimension. Okay, so this is one of the key properties, maybe you can call it a restriction of passivity. So it's applicable only to systems where the input and output of the same size. Okay, so it sounds like a very narrow class of systems, but there are many, many important physical systems and applications in engineering that it's worthwhile to study this seemingly restrictive case. Okay, U and Y, they belong to R. They are of the same size. So that the inner product, this product, we will generalize to the product when U and Y are vectors, the inner product is meaningful. Okay. Set to be passive. Okay. If you can find a continuous differentiable positive semi-definite function. In our example, it was positive definite, but for the general definition, it's enough that it's only positive semi-definite. Function V R and R, and we call such functions as Lyapunov functions when we study Lyapunov stability. In the context of passivity, it will be called, due to some physical motivation, it will be called a storage function. Called the storage function, such that the inner product of input and output, which is meaningful because input and output, they belong to the same space, never less than the inner product of gradient of V, the storage function, with the right hand side of the system. This we can also write as U transpose Y, and this we know is no other than the rate of change with respect to time of the storage function along the solutions of the system. Therefore, another way to write this is simply B dot. And this should hold for all X in Rn and U in Rm. Okay, now we're gonna continue our definition by providing some sub-definitions. Okay. We're gonna now categorize different types of passivity. Okay. In particular, a passive system is further called one of these things if the associated condition is satisfied. For instance, it's called lossless. Okay. If this inequality can be replaced by equality for all X and U. Okay, so lossless if U transpose Y equals V dot. Output strictly passive if U transpose Y greater than or equal to rate of change of the storage function plus a positive definite with respect to Y function. Y transpose rho of Y for some rho to Rn, satisfying y transpose rho y is always positive for non-zero y for all y other than 0. Okay, so that's our strictly passive. And strictly passive. Okay, a more restrictive version of output strictly passive if u transpose y v dot plus some post-definite function of x, okay, psi x or some positive definite with respect to state function psi Rn to R. Okay, so that's the sub-definitions of passivity for a dynamic system. Definition, there's a version of definition for static systems, well, we don't call them systems, I guess, static mappings. Let's also talk about that, and then we will, over some examples, try to motivate these sub-definitions. For memoryless systems, okay, where the output only depends on the input, does not depend on initial conditions, because there is no differential equation used to describe the input-output relation. For memoryless systems, which can be represented by a mapping that relates input to output, U, H, Y, and Y is H of U. We have for we have the following definition. Or memoryless system, or the mapping y equals HU with H is mapping from Rn to the same space is said to be passive. Now we don't need any storage function, so we can just write the condition in terms of u and y. If u transpose y is never negative, lossless if u transpose y at all times equals 0. So geometrically speaking, that means H does, geometrically what it does is it takes U and it generates a new vector, and that new vector is always perpendicular to Y. Okay, so it does some sort of rotation of 90 degrees. Also it may play with the magnitude of the input. So that the inner product gives us 0 for all times. And output is strictly passive. If u transpose y greater than or equal to some post-definite function of y, where y transpose rho of y is never, it's always positive for all non-zero y. For all y different than 0. Okay. So those are the definitions, sub-definitions of passivity for static maps. Okay, now what we're going to do in the rest of the lecture is we're going to apply those definitions, or we're going to see those definitions appear in some very simple examples that we're familiar with. Okay, examples. Consider, for instance, this piecewise linear one port. U is the input, is the voltage applied across the terminals of this connection, and Y is the current extracted by this series connection of an LTI resistor with positive resistance. This is the diode. So let's check whether, for the case where input and output define is that system or that mapping is passive or not. So what we have is for the voltage current characteristics of the system. For negative voltages, okay, this becomes open circuit, the diode, therefore no current can pass through one port. Okay, so for negative voltages we have that zero current. For positive voltages this becomes short circuit, and then this we can simply replace by this resistor only. In that case we're talking about a line, okay, passing through the origin, or a line segment with slope equals the conductance, okay, of the resistor. And then this input output, this current voltage characteristics, okay, give us the following relation between the input and the power, or the product of input and output. Here we have 0 because the output is 0 when U is negative. And for output, when the U is positive, then we have, okay, U over R times U itself. So what we're talking about is we have this quadratic curve. In any case, this product U transpose Y, well in this case U times Y, for all values of the input U is never negative, because all the curve appears in the upper half plane. Therefore, this map is a passive map, or this memorial system is a passive memorial system. As for LTI resistor, okay, that is just remove the diode, you can replace it with short circuit. Plus minus U, this is Y, this is R, U transpose Y. The power of resistor equals R Y squared. Okay. Therefore, its output is strictly passive, because here rho of Y is simply R times Y, and R is passive. Output strictly passive. let's also move on to some dynamic systems. Consider, for instance, this mechanical example, okay, mass spring system. Okay. We have mass that's attached to a wall through a spring with spring constant K. And suppose that Q is the distance of the mass from the equilibrium position. Q is the position or distance from equilibrium, and M is mass, and we have force acting on our mass, our block. U is force. And suppose that we can ignore friction, okay, for the system. Now, let's take velocity as the output from the system. Okay, so y equals q dot velocity. And we can write among what the system is, and q dot dot equals the force acting on the mass, and there are two forces acting on the mass. One of them is due to the spring, okay, and it depends on how far away the spring is from the equilibrium position, and the other force is the external force, U. And what we have is K Q equals U. Okay. Now, the storage function in this physical example can be taken to be the total stored energy, and there are two ways to store energy. One is through potential energy in this spring, okay, depending on the compression or depression of the spring, and also we have the kinetic energy that's stored in that mass. So, potential energy plus kinetic energy, we can write this as 1/2 K times Q squared. This is the energy stored in the spring, plus 1/2 M times Q dot squared. This is the kinetic energy of the mass. Okay. And now, through this storage function, let's figure out passivity properties of the system. V dot equals K Q dot plus M Q dot Q double dot. That equals K Q dot plus Q dot times M Q double dot is minus KQ plus U. Minus KQ plus U. Now this minus KQ and this term cancels, and what we have is Q dot U. And since we pick the output as Q dot, we have Y times U for the V dot. So the product U times Y equals rate of change of storage function for all times. Therefore, according to our definition, this system is passive and passive in a lossless sense. So, the absence of friction yielded this losslessness of the system. Let's see another lossless system, but this time it's memoryless. It's again a system that we're familiar with from engineering. And it's ideal transformer. turns ratio N1, N2. Okay. Now suppose that the voltage that's applied at the first coil is R, one of our inputs, and the current that's applied from the second coil is our second input to the system. And as for the outputs, the first output is the current of the first coil, and the second output is the voltage of the second coil. Okay, Y2. And then what's the relation between all those variables, U's and Y's? Okay, it's an ideal transformer. Therefore, in a sense, the voltage and current is decoupled. This voltage depends only on U1, and likewise, this current depends only on U2. What we have is U1 over N1 equals Y2 over N2. So that's the relation between the voltages. As for currents, we have N1 Y1 plus N2 U2 equals 0. So that's the current and the terminal equation. Therefore, we can now combine these two equations into a mapping from the U vector to Y vector. So Y1 and Y2, which is our output, the overall output of the system, equals the linear function of the input U1, U2. And to fill in the entries of that matrix, we look at the terminal equations. Okay? What's Y1? Y1 is minus N2 over N1 times U2. So we have minus N2 over N1 U2. And it doesn't depend on voltage here, therefore that entry is 0. As for Y2, Y2 equals N2 over N1 times U1, right. It doesn't depend on U2, therefore this entry is 0. Okay. Now this matrix is skew-symmetric, and it turns out that it's very important for this example to obtain the lossless property. Okay, for this mapping, skew-symmetric means that H transpose plus H equals 0, or it equals minus of its own transpose. Now, having figured out the mapping from the output, from the input to output, let's figure out whether this memory system is passive or not. Okay. Since it's memories, we don't have to worry about the storage function. All we have to do is we have to look at the inner product of the input and the output. So let's do that. U transpose Y. Okay. Inner product of input and output equals U transpose times H U. Okay, this is Y, this is U. And now, well, you just replace H with its open form, and it's clear immediately that you obtain 0. But here's another way to see that it's 0. 1/2 U transpose HU plus 1/2 U transpose H transpose U. Okay, since it's a scalar, what we can do is we can just take its transpose. If you take its transpose, you have U transpose H transpose U. Okay, and those two things are equal. Since they're equal, we take 1/2 from this expression and 1/2 from the transpose expression, and the sum must equal the original expression. And this we can write as 1/2 times U transpose H plus H transpose U. Okay, and since H is skew-symmetric, H plus H transpose is 0. Therefore, the product of input and output is 0 for all inputs. Okay? Hence, according to our definition, this memoryless system is classless. Now, here's another physical example. It's water is war. Okay. So we have some sort of container, okay, that we use to store a fluid. Okay. Let's call it, suppose it's water. This is where we feed the water from. Okay. And this we consider as the input is the rate of water that's being pumped through this container. Okay, so its unit is meter cube per second, or meter cube, or tons per day, or whatever you like. Okay. And then as you put water inside, then the level will rise, and that height is our output, and it's measured in, let's say, meters. Okay. Now this is not a perfect container. It's flowed, and its flow is such that it leaks. Okay, so there is some leakage. Because of that leakage, if you wait, you keep losing this water that you store in the container. This is leakage. Okay. Now the model is, if you didn't have any leakage, it's straightforward. A times y dot. Okay. This is simply volume dot, because A is constant. A is the area. Okay. This is the volume, rate of change of volume, clearly equals the input, okay, which is the rate of water being supplied to the container. But this is not an ideal container, it leaks. So we have to introduce that leakage term to our model. Now, it's a very good way to approximate or model leakage in the following way, perspective. Leakage is proportional, okay, to the water pressure, and water pressure is proportional to the height, okay, because this is a uniform container. Therefore, we can represent leakage by some minus alpha y. Okay. And now these two terms together equals the water supply to the system. Okay. Excuse me. This should be on the other side. U minus alpha y. Right. This is plus, and this term is minus, and alpha is positive. Okay. This is leakage term. Now, storage function. Which we can consider as a potential energy of water. V equals A times Y. Okay, so this is the total volume. We can take the density of water 1, so that's the total mass. Okay, this is total mass. Okay, times the distance to the bottom of the center of mass, okay, which is y over 2. times the gravitational constant, which we can take to be unity, of course, because total mass, this is average height. And now let's, using that storage function, figure out the passivity properties of this water system. Okay, what's beta? Beta is y times ay dot. That's y times u minus alpha 1. Okay. Therefore, the product of input and output, u times y, equals beta plus alpha squared y. Okay. Therefore, the system is output strictly passive. Okay. Incidentally, it's also strictly passive because the output is our only state variable. Okay. Therefore, it's not only output strictly passive but also strictly passive. Okay, we have used, even before introducing all these definitions, passivity definitions, a lemma that's related to passivity. So let's remember that lemma. It was lemma 6.5. We used it in our L stability studies. Revisited. Okay. If the system x equals f of xu, y equals h of xu is output strictly passive with the storage function satisfying the following inequality: u transpose y greater than or equal to v delta plus some constant delta. Then you take the norm square of the output, okay, y transpose y, and delta is positive. Then it is finite gain L2 stable, this system, with L2 gain no larger than 1 over delta. Okay, so let's apply that lemma to the very first example that we see in this lecture, that is the RLC network, and we can finish the lecture. This was the input voltage. This is the output, the current. R, L, C. The state variables were the inductor current and the capacitor voltage. For the storage function, 1/2 L by L squared plus 1/2 C VC squared. We obtained the following passivity inequality: Uy was equal to V dot plus the power of the resistor, Ry squared. Okay, now that this expression fits directly to that expression that appears in lemma 6.5. So therefore that equality implies that this system is output strictly passive. Moreover, its L2 gain stable with L2 gain no larger than, in fact in this case it exactly equals, because we can compute that using the transfer function, behavior of the transfer function on the imaginary axis, with 1 over delta. Delta is R here, therefore we're talking about the conductance less than or equal to the conductance of the resistor. And finally, how about the R equals 0 case? Suppose that this resistance is so tiny that we can ignore it. We can take it to be 0. In that case, this becomes u of y, u times y exactly equals v dot u y equals v dot, and then we know by definition that that's a lossless case. And that would be analogous to the frictionless mass spring system in a sense.